We now have an invited speaker, Eric Molines from Telecom Paris Tech, that will talk about adaptive Monte Carlo Markov chain.
Thanks a lot. I would like to thank the organizer for giving me the opportunity of presenting this work. In fact, this work has several co-authors, and I especially work on this topic with Christophe Andrieux from the University of Bristol. So I will start with, this would be the outline of my talk. I will start with a very, very brief outline of MCMC, and then I will skip all this part. I will then move to adaptive MCMC, which is the main topic of my talk. I will present, say, a type of adaptive MCMC which is coupled with stochastic approximation, and then I will end up with an application to time series. Okay, so I will not spend too much time on this slide because you are all, I did not anticipate that there was so much people involved in simulation in this workshop, but obviously there are a lot of. So everybody know here is that MCMC is really a key tool to simulate probability on a large probability space. In fact, it's up to now one of the only means of doing that. Of course, everybody knows also that MCMC depends upon the way you are tuning the algorithm, and this morning there was a very nice presentation concerning how to sample from Gaussian processes that really outline the fact that you really need to design, it's an art to design good algorithm. And of course, Monte Carlo methods in general has become basic tool for inference in complex stochastic process. Because right now I believe that Monte Carlo is ripe to move outside a research lab and to be used in a much more general scenario, we believe that it is interesting to develop algorithms which are able to self-adapt to the problem, and that was the motivation for this research work, which started five years ago, basically. Okay, so what is a Markov chain Monte Carlo technique? Okay. Okay. What is Markov chain Monte Carlo technique? So it's a technique to where you basically you propose new points according to a certain transition kernel, say Q, which is called a proposal kernel, and then what you will do is that you will modify, you will target the desired target distribution by just accepting or rejecting the proposed move. And you will accept or reject the proposed move according to an acceptance ratio, which depends upon the current position of the Markov chain, which is xn, and the current and the proposed value of the move. Okay, and the acceptance ratio is written here. It's a way to write the acceptance ratio. Of course, there are other ways of writing it, and this algorithm is due to Metropolis, so it's something like 50 years ago. This morning we speak about things which were, so it was really in the beginning of the 50s, basically one of the earliest methods proposed to do a simulation, and it has been generalized in some extent, up to some extent by Hastings. Okay, so the thing which is very, very well known, and so as soon as you write the algorithm like that, under extremely weak conditions, sometimes the algorithm will be reversible with respect to the target distribution pi, meaning that the algorithm is prone to converge to this. This means that in fact, if you look at the general theory, there are very, very few constraints that should be fulfilled by the proposal distribution. At some point, it's a good and a bad news. It's a good news because basically everything is supposed to work, at least in the long run, and perhaps in a long run. But it does not give you much advices on really how to tune the algorithm. So today I will basically look at a very, very simple, the simplest algorithm. In fact, I had several adaptation. You can adapt several Metropolis algorithms, but I will mainly focus on the Metropolis algorithm, Where in the metropolis algorithm, what you do is that you propose move according to random walk. So you are starting from xk, and you propose a move according to an increment distribution, q, where q is a symmetric, is supposed to be symmetric. So it's drawn conditionally independently to the past. So that is proposed according to random walk, and then you will just accept or reject this move according to this ratio. So the idea of the metropolis algorithm is simply you run a random walk, and you just bias this random walk by staying at some time at some stage. Okay, so that's the first algorithm I will look at, and the second algorithm I will look at is what they call the independent sampler algorithm, which is very, very closely related to important sampling. Here you are sampling a proposition which are independent from the current state, so it's you don't take into account where you are. Okay, so you sample from a proposal distribution, and then you accept or reject the move according to this ratio. And of course, that's really related to important sampling. So this is where the connection is. Okay, so that was for the first part of my talk. So now I move to what is called adaptive MCMC. And I just defined what a dream, which I took the word by Rosenthal, so Jeff Rosenthal, which worked a lot on in that direction. And what are the objectives of what could be the objective for adaptive MCMC? First, you want to have an algorithm which runs on your computer with very, very little supervision, and ideally would efficiently and cleverly tries out different MCMC algorithms. It will automatically learns what are the good ones, and it will perform a lot of tests to run the algorithm long enough in order to be sure that you are in the stationary distribution. Of course, it obtains excellent means and also interval estimate, because you are a statistician, so you don't want only to have a number, but also you want to have an interval. And also he is able to to report everything that was doing in a clear and concise manner. Okay, and of course the reality is it's easier said than done. So of course, so that's the goal. So it can take 20 years to fill all that goal, and perhaps so until my retirement I have a research program, and this is cool. Okay, so I will start to understand what type of problem that you may have. I will start with a very, very simple example which has been proposed by Jeff Rosenthal, and I will use one of his applet, which is really a very good illustration of the problem that you can have. So here you sample from a state which is only at 6, the dimension of the state is 6, okay? And the distribution of the state is uniform. So then we will modify a little bit that, and what you will do is simply run a random walk metropolis algorithm. So what you do is that you propose according to the current state, you propose uniformly. So the current state is xn. So you propose a move to the right or to the left, okay, according to a distribution which is uniform in that interval. And then, because it's really a random walk algorithm, and this distribution is symmetric, so you will just have to accept or reject a move according to this probability distribution. Okay, and that's it. And this works perfectly fine. We just see how it works. Okay, so this is Java. So now I will just increase a little bit. Okay, so that I don't do adaptations. I just, okay, we look what we're doing here. Okay, so this is, so we restart the algorithm and we run it a little bit faster. So what happened here is that you will not adapting. So you're just proposing. You know, that's a big white point we are proposing, and then you are accepting the move or rejecting the move. Okay. Okay, that's very easy, and you will see that on the long run I can make the algorithm run a little bit faster, and then you will see that the black line will be almost equal to the blue line which is okay. Everything is very fine for that one. Okay, so now I make the things a little bit more difficult. What I do is that I will just modify a bit. Okay, sorry. Sorry. Stop that. Okay, what I do now is I just modify a little the distribution. So now instead of having a uniform distribution under 1/6, I have now very tiny probabilities that 2 has a very tiny probability. So basically so it's really a very simple example, but it is something that happens when you are doing simulation, in the sense that you have two regions of the state space, and these two regions of the state space badly communicate. So it will be difficult to bridge that gap. So of course, so now when you don't do adaptation, so what I can change the size of the interval upon which I am proposing, okay? And if I don't do adaptation, of course, everything will still work, okay? So it's not a problem. So of course, there is what I can show here is that if I just what I can modify as I can modify. Sorry about that. It's a little bit tricky to use because I don't see all the. Yep. P should be P. Okay, so what I can do is that if I modify, so of course on that example, if I modify, I can adapt the size of the proposal under which I am doing the proposition. So if I take a very large gamma, okay, which means that I am proposing between x minus gamma and x plus gamma, okay. I don't even think that there is a gap to fill here, okay, to bridge, but of course I am proposing most of the moves are proposed outside the current interval, which is not great. So what I can do, I can just a little bit. Something like this is correct in the sense that most of the moves now are inside the interval. So and also 3 is much larger than 1. So this means I can move from that part of the state to that part of the state. Okay. And now if I have something which is smaller, okay, then I can run into problem, especially because here if gamma is equal to 1, so here it will. So of course the algorithm is should converge. Okay, but now the convergence will be much slower, okay? The convergence is prone to be much slower because when theta is equal to 1, you know, he has problem to cross this bridge. So what will happen on the long run is that he will have a problem to cross the state 2, okay? Because he will have to problem to accept a move to that state, okay? So it will take a lot of time. And then when he accepts the move, he will stay very long in 1. So of course this means that this value of gamma is a bad idea. So gamma is really too small. Okay, so even you can see that even on this very simple example, the choice of this single parameter is not something which is so easy. And of course it is an ideal case where you can see exactly what you should do, and you should understand exactly why your algorithm is mixing well or why your algorithm gets stuck at certain points. Okay, so here comes the idea of trying to to recap what I've said. So in this example, of course, as I said, as soon as theta here, which was gamma in the previous in the applet, is too small, the algorithm is moving too slowly, okay? So which is bad, and he has a problem to bridge the gap. When the gamma is too large, then he is proposing too much. Move outside the support of the distribution, which is also something serious in practice because that also happened, and it appears that a moderate value of theta, like 3 or 4, which is enough to bridge a gap, and which is where you don't move too far away from the support of the distribution is okay. That's what is called Jeff Rosenthal calls that the Goldilocks principle. So you have this too small is too small, too large is too large, and take just the middle, you know. Okay, so basically people say, okay, why not trying something a little bit more ambitious, trying to make the algorithm, trying to guess what is the right value of this parameter. And here is something which seems to be sensible, an adaptation strategy which seems to be sensible, in the sense that is proceeding like this. So every time a move is accepted, then you increase a bit by 1. In fact, you increase the support of the proposal. Okay. What is this means that if you are proposing that is always true in metropolis hashings, when you are accepting accepting a move is not in general it's good. Also, you need to accept moves sometimes, but having a very high acceptance ratio is in general not very clever, because this means that perhaps you are moving with a very conservative step size. So this is why you say, okay, if I accept a move, then I will increase a little bit my proposal in order to explore faster. And on the contrary, each time you are rejecting a move, you say, okay, perhaps I was too ambitious, so I explore an interval which is too long, and so I will decrease a little bit the support of the proposal. Okay, so basically what you try to, when you increase the size of the support, you accept that the acceptance rate will decrease, and on the contrary, when you decrease the size of the support, then your acceptance rate should increase. Okay, seems to be rather logical and natural, but of course now you should be a little bit careful, because you are no longer in the case where theta is also moving with the set, so you are losing perhaps the ergodicity property, and we will see that this is the case. Okay, so now I do adaptation. Okay, so yes, it adapts. So, and then, yes, what happens here? What happens here is that you see here that on the long run, so that the algorithm, with this type of adaptation, the algorithm will be trapped in the state 1. Okay, because when it does a move, when it is in 1, what happens is that a move to the left is rejected with a high probability. So it tries to every time to keep theta large, because he interprets the fact that it's rejected, the fact that theta is too large. In fact, theta was not large enough in that case. Okay, so this means that the algorithm where you adapt theta here is no longer convergent, because the algorithm gets trapped, and sometimes it's not very. So here now is really trapped. You know, look at that. He's really trapped, and then you see that after 10,000 iterations, the histogram of the run are no longer converging to the blue histogram. Okay, so which is the target distribution. So this means that in fact the adaptation here has a kind of disastrous effect, in the sense that instead of improving the way my algorithm was working, it was working, okay, not perhaps very fast, but it was at least converging to the target distribution. And now because the fact I now move a little bit the parameter at each iteration, then I have even destroyed the algorithm, in the sense that the algorithm does not converge to the target distribution at all. So this is really a disaster. Okay, and this has nothing to do. With so you can produce a lot of different examples. This has nothing to do with the fact that you are sampling on a discrete state space. It can be continuous state space, and there are plenty of examples like that. Okay, so nevertheless, which means that first, when you are trying to develop adaptive algorithm, you should be rather careful, because you really need to preserve the convergence of the algorithm, and the examples below is a kind of warning. So as soon as I adapt the algorithm, I more or less perturb the Markov chain, and therefore I'm not sure that the target distribution pi is a stationary distribution, will be the long run distribution of the draw. Okay, so I need to be careful about that. Okay, and then I will try to understand what type of what type of adaptation will preserve the target distribution. And so this is the topic of this talk. Okay, so what are the key ingredients of an adaptive MCMC? So the key ingredients of adaptive MCMC are basically the same ingredients that something which has been worked out much more carefully, which is adaptive importance sampling. So it's basically a kind of parallel of adaptive importance sampling, but in the MCMC world. So as in adaptive importance sampling, now you will typically have a parametric family of proposal distribution, okay? And that we'll try to do is that you will try to adapt this parameter. Okay, I speak about finite dimensional parameter space. Of course, you can dream of more complex, perhaps functional space, but we don't have worked out this idea yet. So basically, you have a Markov transition kernel, and basically for each value of the parameter theta, this Markov transition kernel admits pi as its stationary distribution. So you have now a collection of Markov transition kernel which are indexed by the parameter theta, and for each value of theta, pi is a stationary distribution of p theta. Okay, and now what you will do is that you will have a sequence. Now the adaptation means that instead of simulating always with the same value of theta, you will have a sequence of value of theta which will vary with the number of simulation theta n. Okay, and this should be what is called in probability as an adapted sequence, in the sense that conditionally, if Gn is a sigma field generated by the draws and the value of theta, so the constraint is that the probability is conditional distribution of xn plus 1 given all the history of the simulation, which is a trajectory of the draws and the trajectory of the parameters, is then conditionally independent. So xn plus 1 is conditionally independent given to the past, and is drawn according to p theta n. Okay, so that's the ingredient of an adaptive MCMC. And the questions are the following. So now instead of having a single Markov chain, I have a kind of bivariate process where xk is the state of the Markov chain, theta k is the value of the parameter. In general, I will choose theta k in such I will choose theta k in such from the algorithm will be that I will consider are such that xk theta k is a non-homogeneous Markov chain. Okay, but xk theta k is a non-homogeneous Markov chain, but xk is in that marginally is no longer a Markov chain. So that's a problem. So nevertheless, what you want to be able to prove, that you want to have to prove that this converge to zero. So in the long run, you want to that this will converge to the target pi of f. Okay, which means that the sequence xk is converging to pi. The law of the sequence is converging to pi. So if you are looking at law of large number, gamma should be equal to 1. If you are looking at iterated logarithm, then n is or central limit theorem, you take n to the power of minus 1/2, and you will then have a kind of limiting distribution here. So we will consider this type of so we will try to find condition upon which this quantity with proper renormalization converge either to 0 or properly normalized converge to, for example, a given distribution if you are interested in constructing confidence interval. So that's the first type of problem that you can ask. The second type of problem, which is much more difficult, in fact, is to be able to have explicit non-asymptotic bound between so the non-homogeneous chain is started at x theta, okay, and you want to have a kind of non-asymptotic bound between the distribution of x at time k minus the target distribution pi at time k. So that can be the total variation norm, and you will if you want to have a non-asymptotic bound, you typically are looking at a bound of this type. Okay, so I should not put TV here. That's really the norm of this difference. Okay, so there is, so what type of assumptions are needed? So you can also, you can weaken this type of assumptions, but basically I think for most applications these assumptions are okay. So what type of assumptions are needed? So the first assumption is that, so what you know about Markov chain is that in order that they converge, so there are several theories, but the theory on which I am working on is a theory where you assume that the Markov chain can regenerate. Okay, so in order to have regeneration in a continuous state space Markov chain, you need to identify small sets, and the small sets are sets in the state space where the probability for all x in that set, the probability from moving to x to a given set A is lower bounded by delta times a probability of moving to that set independently of x. So which means that you have a kind of the probability is lower bounded by something which is independent of x, provided that x belongs to that set. And such sets are called small sets. So here what you assume is that you have uniform small sets. So you have a set C which does not depend on theta and which is small for all the transition kernels. Okay? And delta also should be uniform in delta. And the second condition, so this is typically when you are looking at the theory of Markov chain, these sets are the sets where the chain, when the chain is back to that set with a certain probability which is exactly proportional to delta, you will regenerate the Markov chain. Okay, this is called the splitting construction, which is due to Newman and Atreya and Ney. Also, there are two slightly different constructions on the way you are allowing the Markov chain to regenerate. Okay, and so basically, in order to construct regeneration, to control the regeneration time, so you need to have what is called a drift condition, and the drift condition is just a mean to control the time spent by the Markov chain before going back to the small set C. So here we have considered only what is called a Forster-Lyapunov condition to control this return time, and Forster-Lyapunov condition can be written like this. So you say that now for every theta, p theta v is less than lambda time, and the lambda does not depend on theta plus b 1c, and this in fact can be shown to when theta is fixed. Okay, this theta this condition implies that the chain is V uniformly geometrically ergodic in the sense that you will have exactly these conditions. Yep.
Is that very?
Yes, that's so this means typically that theta belongs to some compact set. Yeah. So that you can weaken a little bit this assumption, but yeah. Basically, theta is a compact set. Yeah. Okay, so what type of general statement you can have in order to guarantee that adaptation will not destroy the convergence? So there is a very simple statement which is the following, which says that assuming that the chain is, as I said, simultaneously strongly aperiodically geometrically ergodic, sorry about this long name, so basically the two conditions before, so there is the same small set for all the chain, okay, and the return time to that set is bounded for all the chain, okay? So that's the first condition. And the second condition is that if you are looking at the total variation distance between p theta n plus 1 and p theta n, okay? So this one is called dn, okay? With dn is perhaps a random sequence because theta n is an adapted sequence, so it's a random variable. But what you will prove, what you will assume is that dn is converging to 0 in probability. So this means that you have what I call diminishing adaptation. So you are away, so you are away. So the thing which is important is not to adapt theta n at the same rate that you are adapting the Markov chain. So it's a kind of 2-time scale, which is not really a surprise. You need to adapt. What was wrong in the first adaptation I did is that I adapt theta n exactly on the same time scale as the Markov chain, and this is why I have destroyed totally the ergodicity. So this condition says, okay, you can do some adaptation, but be careful. You really need to have to adapt much slower than the time scale at which you are drawing the xn. Okay, this is what I call diminishing adaptation. And under that condition, then you can prove that on the long run, the limit in n, there is a mistake here, the limit in n of the distribution of xn starting from x and theta at time 0 minus pi converges in total variation norm to 0. And this is that I can prove. So now, so I restart the algorithm and I do what I call a decreasing adaptation, which means that I adapt, for example, but instead of adapting at each iteration, I adapt every with a probability. So in this decreasing adaptation, I adapt with a probability which is inversely proportional to the number of iterations. So if I am at iteration 100, this means that I will adapt only with a probability which is 1 over the number of iterations. And in such case, of course, the rate at which I adapt goes to 0, which means that when I am far in the when the number of iterations is large, this means that the probability of adapting becomes vanishingly small. And in such case, as I can see, I just have restored the ergodicity of the chain, okay, which I can see here. Okay, of course, you can dream of other adaptation scheme, and I will discuss one of these now. Okay. Okay, so as I said, in the Java applet adaptation, so if I make the adaptation which is such that P of n is equal to 0, at every iteration I just adapt with a probability which is decreasing with n, okay? Then for example, if I choose P n equal 1 over n, this means that on the long run I will adapt an infinite amount of time, so because the sum of this probability is equal to infinity, so which means that on the long run I will never stop to adapt. But of course, because the rate of adaptation is going to 0, then I will converge according to my general statement about diminishing adaptation property. Okay, so I will skip that example. And I will, okay, what I will describe now is a general, so that gives me some ideas on the way to adapt, and I will just describe an algorithm to do adaptation which is perhaps more generic than the one saying, okay, you can do adaptation simply by trying to doing adaptation, but every 1 over n iteration with a probability which goes to 0 with the number of iterations. So I restart with the Metropolis Hastings algorithm, and what I will try to do is, so the influence of scaling is obvious in that case. So in general, in Metropolis Hastings algorithm, there are two problems. The first problem is that, exactly like in the finite state space example, so either you do very small jumps, and if you do very small jumps, your algorithm always accepts the move because the ratio is very close to 1 if pi is a smooth distribution, and in such case, because you always accept, you are exactly having something which looks like a random walk, okay? Because what makes the difference between Metropolis algorithm and a random walk is the fact that sometimes you just stop the random walk, okay? So if you always accept, this means that during with a high probability you have stretch of simulated data which looks like a random walk, which is not very ergodic. Okay, so that's two small step size are not okay, and of course the other problems with Metropolis Hastings and where the step size become too large, and when it becomes too large, this means that the jumps are so on the contrary, the ratio of acceptance ratio becomes very small, and the moves are accepted only with very, very small probability. So the proper time scale is, so finding the proper time scale in a Metropolis algorithm is something which is badly needed. So I just show up what could be something where here the step size is too small, and you see that the algorithm looks like a random walk with a very, very strong positive correlation, okay? And if you look at the correlogram, you see that the correlation vanishes to 0, but at a very, very small rate. Here it's a way where you are doing jumps, but too large, so which means that because the jumps are very large, you are also very high correlation because you stay stuck on state for a very, very large amount of time. And this is the algorithm which is correctly scaled. Okay, so when starting from that, you say, okay, I will try to try to adapt the scaling. If that's at least one of a parameter I can adapt, that's the scaling of the algorithm, and so I can try to find several criterion. And the criterion, perhaps the first criterion you have in mind, you say, okay, a good idea would be to minimize, for example, the long run covariance of this estimate. Okay, so you can of course write the stationary covariance of the estimate of the mean of a function f. It is written like this. Okay, and you say, okay, this will depend typically about the scaling parameter sigma, so I can perhaps try to minimize this quantity. The problem is that this is extremely difficult to estimate. So that there are two problems. First, it's very difficult to estimate, and second, it really depends on the function you are looking at. And when you are doing Bayesian inference, you are in general not looking at a single function, but at a set of functions. So it's not totally clear why this is of interest. Okay, so of course the estimation of the asymptotic variance is very difficult. And the optimization is also very difficult and depends on the functional. So this is why several other attempts have been done in order to obtain meaningful optimization criteria. So the common idea in mathematics, when you have a difficult problem, is to try to try to solve a simpler problem or a much simpler problem, but which keep most of the features of the original one. Okay, so this is basically I will spend perhaps some time on this. So one of the approaches which have been very successful in analyzing metropolis hashing algorithm, which is due to Garrett Roberts and several co-authors, but I think that Garrett was really the one which was looking at in that direction, was to try to understand the behavior of the algorithm when the dimension of the state space becomes large. Okay, there are several. So there are several ways. So a natural way to analyze a Markov chain is to try to make some asymptotics in order to obtain at the limit a simpler algorithm. Okay, simpler like diffusion or ODEs or things that you can really understand. So the one what I will describe here is what is called the diffusive limit. So in that case, what you are supposing to look at, you are trying to sample from a distribution, okay, pi of d. So now it depends on d, which is the dimension of the state space, and this distribution is assumed to be the product of that. As I said, it's a very, very simple one. So it's the product of independent marginal. So with f is a one-dimensional marginal. So of course it seems a little bit far-fetched. I mean, okay, I will try to sample in a space on a distribution which is on r to the power d, but I sample a distribution which is very simple because it's a product of one-dimensional marginal which are independent. Of course, you can look at more complex models. I will say a word about that later on. But of course, you can still say, okay, what will happen if I look at this, okay, and if I try to optimize the scaling? For this, for metropolis algorithm, using pi of d as a target distribution. So what I will do is I use a metropolis proposal. So this time the metropolis proposal, this is a proposal of the increment of the move. The metropolis proposal is here a normal distribution which is theta square. So that would be my parameter divided by d. Okay, which is the dimension of the state. So you are willing to sample with the metropolis algorithm this distribution, and you do a proposal according to this normal distribution, okay? And you scale everything properly in order to obtain a limit. So in order to obtain a limit, you look at this, what I call interpolated process. So this time it's continuous time processes which depend on D, okay? Where what you do here, you scale also the time. So you are looking at a single component, okay? So you have the chain lives in R to the power D, but you are looking at the first component, for example, of that chain, okay? And you are speeding up the time by a factor T times D, okay? So ZTD is a one-dimensional process, okay, which is obtained from the Markov chain simply by looking at the first component of this D-dimensional Markov chain and speeding up the time by a factor D. And what happens, which is not very surprising if you are looking at this, is that there is a kind of decoupling. That means this is a kind of large mean field type of stuff, in the sense that in this asymptotic, a single component of Markov chain is the average of the others. And this means that all these one-dimensional components start to become more or less independent and see the mean level of their friends. Okay, so that looks like this. So okay, if D is equal to 5, you can still see the jumps, and then because when you increase the dimension D, there are less jump, and the algorithm and the trajectory becomes to look much more like a diffusion. Okay, and what you can prove, and which is, as I said, not very surprising, what you can prove is that Z of D, which is this one-dimensional, this one-dimensional process converges in low to Z, to a process Z. So the convergence occurs in the space of CAD-lag process. So it's score called D0. Sorry, the D01 space. Okay, that's not a big problem. So it converges in the right topology to what is called a Langevin stochastic differential diffusion. So it's a Langevin diffusion, and the Langevin diffusion is written here. So dBT is the Brownian motion, of course. V of theta is the diffusion terms, and this is the gradient of the one-dimensional target. That means the distribution is a product of one-dimensional distribution, and V of theta is a function of theta, where phi is the distribution function of N01. And not surprisingly, the I which appears there is simply the feature information of the translation model, and which is just something which is linked with the fact that you see the means of the others. Okay, that's why you have this Fisher information appearing here. Okay, so now V of theta is the speed of the diffusion. Okay, you can just change the time and obtain a kind of, write Z of theta, Z of t as Z tilde of V theta t. Sorry about that. So V theta is exactly, you have a single diffusion which is Z tilde of t, which is a normalized, time normalized Langevin diffusion, and V of theta is the speed of the diffusion. Okay, so these diffusion are of course stationary. They are ergodic. The limiting distribution is F. Okay, and so the idea, in order to have the algorithm, the faster algorithm is the one which maximizes the speed of the diffusion. So in this limit, you can say that there is you can define what is the faster algorithm is the one which maximizes the diffusion limit. Okay, so there is a very nice. So okay, that's a nice result, but there is an ever nicer result. The ever nicer result says that this speed of you can write this speed of diffusion, okay, by as a function of something which is called the mean acceptance rate of the algorithm. So what is the mean acceptance rate of the algorithm is when you are in the stationary regime, okay, you are looking at the number of time you are accepting the move, okay. So that's, if you look at this is a distribution of x, which is a current state, which is in the stationary distribution here, and y is a proposal state. So this one is a joint distribution of x, and which is a current state, and the proposal state, and this is the acceptance rate. Okay, so tau d of theta is the mean acceptance rate. Is the number of times you will accept in the long run the move when you are in the stationary regime. And when d is going to infinity, then you can prove that this mean acceptance rate converges to a certain limit, and this limit is precisely is related explicitly with the speed of the diffusion. So now, what is the next step? The next step is to say, if I want to obtain the fastest diffusion terms, then I have to optimize the acceptance rate. So it suffices that I optimize the acceptance rate in order to maximize the speed of the diffusion. Okay, and then you obtain that. So what you do is that you say, okay, if I optimize this with respect to the acceptance rate, I find a kind of magic number. So the magic comes from the fact that it's very simple. It's 2, 3, 4, but the next is not 5. So Gareth always show the first 3. Okay, so that and from that you can deduce that there is an optimal value. The optimal value of the scaling is the one which is such that the acceptance rate is equal to this target acceptance rate. Okay, so then this is a very nice analysis in the sense that it provides you, of course, at a simple model, but you have a definite answer which says, okay, the right things to do when you are doing a metropolis hosting in large dimension, provided that you have this kind of a specific form for the target distribution, but this can be generalized a lot. Okay, in fact, which is really needed is the fact that you end up in large dimension with a regime where the stationary distribution can break into more or less independent blocks. That's the truth. And then you know that the optimal tuning of the parameter should be such that the acceptance rate in the long run should be 0.234. Okay, so I've done things the pros and cons. So as I said, of course it's a diffusion limit. So empirically it works. That means having when you are doing metropolis, it's a good advice to have something which is between 20 and 30% of acceptance. In general, you are not totally wrong. There are many improvements, and in particular, there is a very nice PhD thesis written last year by Mylène Bédard, which is Canadian, French-speaking Canadian. So you should read her thesis, which makes several extensions of that. Okay. It's very interesting, and in fact, she rewrites very carefully some arguments which were written in a statistical science paper by Roberts and Rosenthal, but where the technical details were a little bit just put under the carpet, and she really makes all the points very clearly. Okay. Okay, so now the idea was to say, okay, is there a way to control? So now I want to try to say, okay, what I want to do is to adapt my algorithm in order to obtain an algorithm which is adaptive in a sense that it automatically reach this acceptance rate. Okay, so what I will do, is a very simple algorithm. I will try to formulate the problem as a stochastic approximation problem, where the objective is now to find the value of theta, which is such that this value of theta will solve this equation. Okay, so tau bar is the target acceptance rate, so it's a 0.234, and I will try to solve this equation with respect to theta. Okay, so this is typically, so of course this you cannot compute this expression. Okay. So of course you can say, okay, well, how can I do that? But if you know a little about Robbins-Monroe type algorithm, of course that's exactly what Robbins-Monroe can do, in the sense that you cannot compute this integral, but you can compute, of course, the integrand. and that will be the aim of this algorithm. Okay, so what I will do is I will write a kind of Robbins-Monroe type algorithm where at every time I look at this quantity, which is the acceptance rate minus tau bar, as a kind of noisy observation of this objective function. Okay, and I end up with an algorithm which works like this, where at every iteration, what I propose according to x k plus theta k n 0 I, okay, and I accept now this move. So I accept this move with a probability which is this acceptance rate, okay, and I update theta k according to this expression, to this relation. And what I see here is that if you remember what I said before about the decreasing adaptation, so here the adaptation is decreasing because the step size at which you are modifying theta k is going to 0, okay, and in such a way that this should go to 0, but still this will be infinite. So this means that it's another way of having a diminishing adaptation, in the sense that what you do here is that you are the increments between theta k and theta k plus 1 are controlled by a certain gamma k, okay, a step size which is going to 0. So instead of adapting rarely, which was what I suggested before, you adapt at every iteration, but the amount of change on the parameter is now controlled by a quantity which is deterministically converging to 0. Okay, that's a plot to show that this algorithm works fine. So according to the dimension, and what I did here is something which is to show that this algorithm works even if you are not necessarily in the case of where the pi is simply a product of independent marginals. So it is done on a more complex unimodal target, and what I show here is I vary the dimension, okay, and I just look at the correlation, the correlogram, okay, for optimally tuned algorithm. So an algorithm where I have find the optimal parameter by a kind of trial and error, okay, and this one is a plot of the correlogram with adaptively tuned value of theta, and I can see that there is a pretty good match. Okay, so I will have not time to so there are of course other idea. We just don't spend time, and this is one of a very simple algorithm, in fact, where you do that, but you do something which is a little bit more ambitious, just to give you another idea of how you can couple adaptive MCMC with stochastic approximation. So the idea here is that you adapt. So here, before we adapt only the rate at which you are you adapt the scaling, okay. But here we adapt the scaling, but we also adapt the covariance of the distribution. So what you can show is that under appropriate condition, okay, you can prove that the optimal target should be, so if you have a kind of elliptically symmetric distribution, so if you want to sample to a kind of elliptically symmetric distribution, what you need to do is that you need to sample with moves which has exactly the same covariant structure than the target distribution, which makes sense, but with a smaller scale. So if you want to sample to for example a Gaussian distribution with a target covariance gamma, then you need to sample the instrumental distribution should also be Gaussian, but with a covariance which is scaled, of course. Okay. So this you end up with an algorithm which was originally proposed and more or less independently. It was one of the really first attempt to do adaptive MCMC. This algorithm was proposed by Arios, Saxman, and Taminen in a very nice paper in 2000, and there is also a follow-up paper in 2005 in GRSSB. And the algorithm works like this. So this time you propose, so you will propose move according to a Gaussian with a covariance gamma k and a scaling sigma k. Okay, so this is a proposal distribution, and you will adapt both gamma k and sigma k. So you adapt gamma k by just computing the according to a stochastic type approximation procedure. You are computing the covariance of the samples that you have already drawn up to time k, and then you adapt the scaling by just adjusting the acceptance rate. And it proved to be very effective. So here I look at a very simple example where I try to sample from this Gaussian distribution in dimension 12, which is not much, and the condition number is not terrible. It's 100. Okay, and I start here with I sample from an isotropic normal distribution with the optimal scaling. In that case, you can, if Q is isotropic, then you can compute exactly what is the optimal scaling from it. And what you see here, you see that here are the two components, and there are the points, and here there are 1,000 points, and you can see on that plot that you don't move much in the space, okay? And which is clear because since you are sampling with this, okay, this means that there are many directions where you fall outside the support of Q. And as I say, in dimension 12, a condition number of 100 is not something huge. In fact, it's and now that's the algorithm with the adaptive, with the optimal covariance. So now with the optimal covariance, what you do is that you sample, instead of sampling with standard multidimensional Gaussian distribution, you sample from this quantity which has the same covariance as the target distribution, but scaled by something which depends upon the dimension. Okay, and then you see that it is much better mixing. Okay, you can see that it is much better, and the correlation also is much better. And this is what you obtain with your adaptive MCMC algorithm. Okay, so I will not have time to. We not have time to go so if you are interested, we had an example of this to do some kind of inverse problem, but I think I already speak too long. So there are many different means of adapting. So there have been proposals, for example, to adapt the size of blocking in GIP sampling. This morning in the talk about Gaussian process, you can also imagine that you can adapt the control point, the auxiliary control point. So there are many ways to adapt. Of course, there are several. So it's difficult to imagine. So when we start this project with several friends, we had the project to end up with a kind of very convenient software where you can play a little bit like with WinBugs. You just specify the distribution, you press a button, and that works. So it's not exactly like that, but you have, for example, several adaptive procedures which have been developed, especially by Jeff Rosenthal, which is quite nice if you want to try it. Okay, thanks for your attention.
We have time for a few questions.
This is actually, I mean, you touched on so many things that sort of one of your earlier remarks on the that one wants to get bounds on the rate of convergence and now, but often, my understanding that often those constants are rather large.
Yeah.
So that the bounds or the rho is quite small, or, I mean, quite large. And so, so there's sort of the, if you want, the more point of view coming from more classical statistics, which is rather than trying to get absolute bounds, which are maybe best suggestive, you try to use the data and to sort of give yourself an idea of
Yeah.
where you are. Is that at all possible in these kinds of cases?
There are two questions. So first, the bounds. So the bounds are obviously extremely, in general, especially if you are in a large state space, it's almost hopeless to use bounds obtained from regeneration and this type of coupling. And we know tighter bounds, but for example, when you are looking at very, very specific structure on hypercubes or random walk metropolis on hypercubes, there were bounds which are much better, which have been developed by Diaconis and which just rings. So, but using really combinatorics algorithm, it's really a totally different way of looking at obtaining bounds. So this means that there is some hope that the bounds are poor. Okay, but in general, that's another comment. So it's not reasonable to say that I will sample in 1,000 dimensions. So the bounds are poor because the way we are constructing the bounds are extremely primitive. Okay, because you just look at a small set, and obviously when you are in a very large dimensional space, it's the time to reach a small set is very, very long. But sometimes when I see presentation where people are sampling in very, very large dimension, I think that okay, that's not sensible. So there is no mystery, you know, that you cannot do much with that. So the second point is that is it possible to have a kind of diagnosis of convergence? And this has been a subject of interest in the 90s. There are several tools to do that. In fact, the conclusion is that it's very difficult to make diagnosis from a single run. So in that case, it's much better to have a kind of parallel MCMC algorithm, okay, and trying to understand what happens when you are looking at several runs of shorter sizes, and you can make some diagnosis around that. Yeah.
Actually, I mean, of course, this issue of high dimension is one that's this conference or this program is focused on. And one of the themes, at least, that I've found attractive is that if, in fact, you are genuinely in high dimension, and you have a distribution which really fills the high dimension, it's hopeless anyway. And so. And I think you were alluding to that actually towards the end. Strategies where you basically look as you move along that really things are living. They're not at all Gaussian, and they're living on low-dimensional structures.
So that, in fact, that's of course that's the. So that was the point also of the talk this morning, where you are looking at Gaussian processes, but. So the number of the set on which you are sampling are infinite dimensional space because you are sampling on the space of function, but in fact you are living in very, very low, so that's true. And at some point what a good algorithm should do, and we are not able to do that right now, is here the best that we can do is with adaptive MCMC is to try to capture something like a global, like the algorithm I described, with kind of global scaling. And in fact, it does something very sensible, which is at least you are not, if you are variables which are small and other which are large, you are sampling with almost the correct size in every direction. Okay, but of course, if you imagine more complex problems, it is not sufficient to use this a single proposal for every part of the state space. So you really need to try to adapt to something that can be local correlation, whatever it means, because it becomes difficult to because then you are in the problem where you need to divide the state space in more or less clever manner in order to understand what are the behavior of the target distribution in that space and things like that. And also the problem is that you should be very careful with it when adapting, because, for example, I had also an example where we do adaptation. You have the problem of over-adapting. So when you are for example, you have a bimodal distribution or in say, not in R is a very simple case, but in R3 or R4, then the algorithm becomes very pleased because they see a kind of mode, and then adaptation can reinforce at some point, and you even get bad time to visit. So there is a little bit the same problem like in machine learning, where there is a kind of a competition between discovering new features and trying to exploit what you have already seen. And that adaptation in that case is because when you say, okay, everything is safe if you diminish the rate of adaptation, that's asymptotic. Because it doesn't tell you, so in the long run that's true, but that does not tell you the rate at which you should decrease the adaptation. And of course, if you are in large dimensional space, you should let the algorithm discover features before trying to freeze or to over-adapt to some specific features. So this is why I think it's a nice idea, but there are still a lot of work to make this idea work. Say generally for many problems. Yeah.
Any more questions? Then we thank our invited
Thanks a lot.
speaker again.